going to sound like science, believe it or not. A lot of this is going to sound like what you guys did in science as far as reasoning, hypothesis, things like that. So one of the things that we talk about in math, in science they kind of call it a hypothesis. A hypothesis is just an educated guess. In math we call it a conjecture. They kind of mean the same thing, all right? I guess, let's see, we'll do an example. If I'm trying to make an educated guess of some sort of scenario, I'd probably look outside and say, it looks pretty crummy out. And just by the idea of why do I think it looks crummy and or chilly and raw is because the ground is wet. You can see the wind is blowing around. There's raindrops on the window. I'm just using things of that I'm observing at the time as far as what is going on. So just looking outside, you guys understand what I mean by, it's kind of raw and crummy out. I mean, it may not be 30 degrees and rainy, it might be 60 degrees and rainy, but still it just seems like it's crummy. And the reason that I'm coming up with that idea, because like I said, I'm looking out there. It looks like it's wet. It looks like it's windy. It looks like it's rainy. Things like that. And to me, that doesn't seem like a very pleasant day. Make sense? You guys do this all the time. You make individual conjectures about every single situation you come across, whatever it is. You probably walked in your head, you probably had some preconceived notion of me as a teacher when you walked in. You might have heard things. You might have saw me standing there. You might have heard me yelling at you or yelling at somebody else, say, oh man, this guy's a jerk, and then all of a sudden he's awesome now. But, things like that. What we do here is you are using what's called inductive reasoning. You're using all these conjectures that are based upon specific observations. My conjecture, my idea, my hypothesis that it's cold and raw out because I see the wind, I see the rain. You can kind of almost get the sense that you don't want to be outside. That's what you call inductive reasoning. You're trying to come up with some sort of rationale as to what's going on. Okay? You use it. You guys ever do what's called hypothesis testing? I think don't they do that in like a science where you try to guess weights and things like that? You look at an object, try to you see how large it is, try to figure out the weight. I mean, look at the pyramid up on top of the cabinet over there. You look at that and you start thinking, all right, that looks like it's metal. So it could be solid, it could be somewhat thin. An educated guess as to how much it might weigh, could weigh 2 or 3 pounds. It could weigh 10 pounds. You're just trying to get the idea of perception, right? If I look at Mr. Leone, if he stands up, I can say, I'm guessing he's about 5'2", maybe 5'6", all right? And that's just an educated guess because I know how tall I am, and if I walk by him, I can kind of get a guesstimate of how tall he is, things like that. You can do these things, okay? It is not. You actually also do this when you have multiple choice questions. Think about the one that was on the test, about the angle. You had to get an approximate of a 72 degree. Well, you know what 90 is. Is 72 bigger or smaller? That's all you're doing. You're inductive reasoning to get that question. All right? That's all that is. All right? When you go through things like this, you've seen this before. Well, not this particular sign. I don't think you've been to this zoo. But if you read a sign like this, what is something you can say about what's going on? What situation? Yeah. Be safe, right? I mean, I think this is great. Be safe. Don't sit, stand, climb, lean on the zoo fences. If you fall, animals could eat you, and that might make them sick. Thank you. So what do they care more about?
The animals.
The animals. They care more about animals than they care about you, because you just implied that from what they stated. You're looking at your surroundings. You're looking at a bunch of different bits of information to come up with that idea. That's what you do. That's inductive reasoning. You're just trying to make that educated guess. Those of you guys I see you walking around in pajamas today, I bet you, my guess is that you're probably pretty comfortable. Okay? All right. Same idea with this. What can you say about this picture?
He's safe.
No, the baby's
The baby's really cool. Okay.
straight
What
bullet.
makes you say that? Because of the awesome sunglasses. Isaiah, what do you got?
That baby is in a safe position.
He's in a safe position. Why do you say that?
He has like a life vest on and he's sitting there and yeah.
Okay.
He's on a
Where-
boat
He's on a boat. Why do you think he's on a boat?
because of the seats.
Yeah, because of the seats. You guys probably recognize that. Yes, sir.
That baby's Caucasian.
That baby's Caucasian. Very smart. Yes. Okay.
That girl has some good calves.
Okay. Great. But
Just
the
they have
idea
pink
here is
toenails.
that you were able.
Just
The idea again here, guys, is that when you see a situation, you're able to come up with ideas about it. Now, do you need paper or pencil or anything?
She was talking.
Oh, okay. So you're coming up with these ideas, and you're right. He's on a boat. He's a white baby on a boat. He's cool because he's got sunglasses on.
He's straight bullet.
What's that?
Straight bullet.
And he liked Cheetos.
Do you see Cheetos somewhere?
He looked like he liked Cheetos. Not regular Cheetos, but the puffs.
I. That's awesome. I'm trying to think. Yeah. Okay.
He's kind of holding his left hand, like kind of like this. You know, like you have like
When you have Cheetos.
Oh. Okay. Now, go into a geometry thing then. Go to a geometry situation. You do the same exact thing. You can make inferences. You can come up with ideas. You can come up with situations that occur when you're given a specific statement. In this example here, you are given points A, B, and C. And then it gives you segment lengths. It tells you that AB is 10, BC is 8, AC is 5.
Wait.
Make a conjecture. Come up with some idea and draw a diagram about it. Come up with some idea and draw a diagram. Come up with an idea that's going on there. Now, I know a lot of you guys, you're saying it makes no sense. Well, why?
Is it a triangle?
Because if AC is a
Oh, it is.
and it's
Probably,
Oh.
whatever.
Can you just jump right out and say that does it say that they're collinear?
nope.
No, it doesn't. And you're going through that. It doesn't say that they're collinear, but couldn't you just do that?
Charles Rager.
All right. And that's the idea. Yes, ma'am. Oh. The idea here is, guys, that not everything has to be what you think it is right off the bat. It doesn't have to be collinear. That was a conjecture that you could make. You say, oh, my idea is that they're collinear. And I'm actually kind of glad that you guys came up with the idea that you thought they were collinear. And I'm going to use that as the following example. So let me put this on a clean sheet here real quick. If your idea was that these guys were collinear, so your conjecture, A, B, and C are collinear. So if that's your idea, here's what I'm going to do. I'm going to use what's called a counterexample. A counterexample is anything that disproves a conjecture. I'm going to use what's called a counterexample. Counterexample is anything disprove a conjecture. Again, think about it like hypothesis testing or whatever you did in science. If you came up with a hypothesis and you wanted to disprove your hypothesis, you could just come up with some, only you had to show one thing that it didn't work. Anybody? All you have to do is show one reason why it doesn't work, and that disproves something. So my idea here a second ago, when I said, oh, Leon's 5'2", that's my conjecture. How can I disprove that? By measuring, yeah, actually get a tape measure and measure. And that's how I can disprove it. So here, if I want to say that they are collinear, the way that I can disprove the fact that they are collinear is by the following. Well, according to my diagram, or according to my given statement, it says that AB is 10. And then it says that BC is 8. If that's the case, if these guys are collinear, what would AC have to be? It would have to be 2. It won't work because it says that it's 5. And last I checked, 5 plus 8 does not equal
10.
Right, it equals, very good. 13 doesn't equal 10. That's a way that I could disprove that statement just by a very simple counterexample. Okay? You know how you guys use a lot of times in math, we use examples all the time to show how math works? Solving equations. How many times do we show examples on how to solve equations? A lot. And we do that over and over and over again. Well, counterexamples are just to show that something doesn't work. That's it. That's really all it is. Okay? Do you guys remember the experiment when you deal with the science where they say that if you drop two things will fall at the same rate? Two things will fall at the same rate, same speed if they're in what's called a vacuum. Remember what that means? There's no if the atmosphere, if the air resistance is negated. So a feather and a bowling ball will fall at the same negative 9.86 meters per second squared. That whole thing. That's the whole idea. You know, you can prove how something works along those lines. Okay. What's that? Does it weight? No. Two weights don't matter. Two things will fall at the same rate. Exactly.
Gravity.
Gravity. These two things way different.
So a bowling ball and a feather's gonna float.
Negate
No.
air
The
resistance.
vacuum.
Get rid of the air resistance, and they'll fall at the same rate.
That's really
It's the same thing. You and Bobo don't weigh the same, do you?
not at all.
Both of you guys stand on your chairs and jump off.
Look at them, they excited to do something like this.
1, 2, 3.
1, 2, 3.
Well,
We
you didn't
jumped
jump at the same time, but see the idea, you fell at the same rate. Should we all do that?
Yes.
Levantate! Alright. Come on, Sarah! Ladies, come on!
Off your butt.
Alright, so at the same time, we're all gonna go off, don't land on each other. We're gonna really annoy who's downstairs from us?
Mr. Solomon.
No, he's on the other end.
No.
Alright, so it's gonna go.
Oh, it's Albrecht.
Alright, we're gonna go 1, 2, 3, jump. So it's 1, 2, 3, jump, okay? 1, 2, 3, jump! Okay, it works.
Where did they do it upstairs?
I did.
Where's the hell you
I did. We need to do a second experiment.
Okay. All right. Go along the same example, same idea. Is this true or false? Statement. My generic statement to you is the following. X, Y, and Z are collinear. The conjecture that I'm going to state to you then is that X is between Y and Z. True or false? If it's false, give me a counterexample. Draw a diagram or write it out. Explain it. Take a second and see if you can come up with something. Whether it's true or false and why. When you guys all did that, I saw her kind of like that.
Her what?
She kind of jumped. We scared her. So, what do you think? True or false?
True.
All right, who says true? Okay, who says false? Well, I'm agreeing with the false people.
Well,
Because why? Because look, does it say anywhere in this statement that they have to be in a specific order?
No.
No, it just says that they are collinear. If 3 points are collinear, that means though if we don't know the order in which they are written, we can write them in multiple different ways. So if the only conjecture that I came up with that was that x is between y and z, couldn't I also do this? Aren't those still collinear?
yeah.
Yeah. It doesn't necessarily state that they're in a specific order. So I would say that this is false, and my reason behind it is that diagram. Listen to this statement. If you are a teenager, then you are 15. True or false?
False.
Why?
Because teenagers, any age from 13 to 19.
19.
Correct. That's a counterexample. You can disprove a statement. Now what about this? If you are 15, then you are a teenager.
Correct. Correct.
True. I don't have to mess with that at all, do I?
No.
It works just the same. Okay. So let's look then at where we come up with these if-then statements. You guys ever heard of if-then statements before? Okay.
If we like the match at 12 o'clock, it will burn out at 12. Then it'll burn out at 12.
Okay. So what does the if and the then stand for? Do you remember?
Oh, I know.
Cause and effect.
Kinda, yeah. Cause and effect. Cause and effect is a good one to look at, or hypothesis conclusion.
Every trailer Chicago.
That's all it is, man.
60 miles per hour.
So, like I said, I'm mixing a lot of this chapter. I'm going to kind of blend things back and forth. Today, I'm going to mix it up between 2-1 and 2-2. Tomorrow is all 2-2. Friday, like I said, I am planning on doing all logic puzzles with you guys that day. I like to split you guys into groups and have competitions about who can figure it out faster. And then when we get back from the weekend, we will start with what are called algebraic reasoning proofs. We will spend 3 days on that and then take a short quiz on it next Thursday. Then we have a 4-day weekend. Then we have a 4-day weekend because of Columbus Day. When we come back from Columbus Day weekend, then we will start then in chapter 3 with some of the parallel lines cut by transversals. Like I said, we mix things around a little bit to move through these first couple of chapters, okay? What's that? It goes real fast. Yeah, once we get back from Columbus Day, then it's like a straight block almost until Thanksgiving. So, if-then statements, just like you were saying, we start with what's called a conditional statement, and they have two parts. It's called a hypothesis and a conclusion, cause and effect, if you want to think of it that way. Real easy example. If it's 4th hour, then you are in geometry.
False.
Not for everyone.
Good call. If it is 4th hour, then Nigel is in geometry.
True.
That's true.
He could be skipping.
That's true.
That's false. I don't skip. My mom would smack me.
So that's the idea, guys. You have these conditional statements that we use with an if-then form. Now, one represents the hypothesis, what you're trying to show. The conclusion is what happens. Okay. And you said you use this in biology?
Yeah.
Okay. So let me show you an example that I used first hour. If two angles are adjacent supplementary, then they form a linear pair. True. If two are bringing out the inner unicorn. If two angles are adjacent supplementaries, then they form a linear pair. True or false?
True.
It's true. Okay. It's true. If you look on the whiteboard over there, isn't that two adjacent supplementaries?
Yes.
Yeah.
Don't they form a line?
Yes.
Okay. So what's my What's my hypothesis? What's my cause? What's that? What is it?
You said what?
What?
You making me confused, because I said you said what, then you said what?
What? All right. Again, what is your hypothesis in this part? What's your if?
The two angles are adjacent.
Adjacent.
Something
Yeah.
like that.
So the cause, like you called it, there's your hypothesis. What happens when that is true? They form a linear pair. Okay? You will see lots and lots of geometry definitions written in this if-then form. Okay? It's an if-then. For example, if an angle measures 90 degrees, then what is it? It's a right angle. If an angle measures 90 degrees, then is a, oops, I can't write today. And we've had that definition before. If you think about it, we've talked about it. You've seen this. If an angle measures 90, then it's a right angle. Hey, can you say that backwards?
If,
The measure.
Go on, say you had it.
Tap.
if at a right angle it equals 90 degrees, then you have a 90-degree angle.
You're overcomplicating it. If I flip-flop these two,
Oh.
if you have a right angle,
Then it's 90 degrees.
that's it.
Okay.
That's it. So a lot of geometry definitions, and we're going to use a lot of this probably starting tomorrow with some of our conditional statements that we're going to look at. A lot of times what will happen is that definitions and theorems and things like that in geometry can be written forward and backwards. It works going both ways. It's what we call a biconditional statement. Don't write that down now today, but it works going either way. If an angle measures 90, then it is a right angle. If an angle is a right angle, then it measures 90. It's true going both directions. It's one of those things that we use a lot of in geometry. Just want to give you guys a little heads up on that. The other example that I had for you then was, oh wait, real fast. We'll use this more tomorrow as well. When we use these if-then statements, I always use the straight logic form of writing these out. P's and Q's. You ever heard the term mind your P's and Q's? That means use reason. That's what it meant. It meant use logic, use reason, mind your P's and Q's. Use your brain. Think about what you're doing. That's what that old statement stood for. So what we use for, I do this a little bit different than other teachers. When I grew up doing logic stuff, we always had a P for the if, a Q for the conclusion. And we used it in high school, I used it in college for different courses as well. Your book does a little bit of the P and Q, like one page, but I think it's pretty easy to follow through. So P is your hypothesis, and this is your conclusion. All right. You have P and Q. Yes, sir.
You ever heard Lil Uzi Vert?
Who?
He's trash, you're trash.
No, he's not.
No.
You know you're getting marker all over your head, right?
You couldn't see it, just your hair. Hey, go to the bathroom.
I don't think
No, that was may I?
Down.
Is that a yes?
Suppose you want me to carry the desk now, too.
Yeah.
So is that yes?
Just throw it, I guess.
Mr. Murphy,
What?
can I ask you a chance to write?
Oh, you're trash.
Oh, he's trash.
Wait, can I
You
go?
do?
Nigel is trash.
You ever hear Little Moo?
Where you go that?
I'll be here.
So, like I said, we'll use more of this stuff tomorrow about the whole truth statements here. But you've all seen this. You've all heard this statement. If this had been an actual emergency, then the signal would have been followed by official information. You know, when they set out the alarm systems and stuff, you know, the tornado siren, or when they're doing the practicing on TV, you hear it on the radio, things like that. What's the hypothesis in this statement? What's your if? What's your P?
If this had been an actual
If it was an emergency.
and then the conclusion, it would have been followed by official information.
Exactly.
Wait,
Yeah.
weren't we supposed to have like a training last week?
Yeah, but there was a lot of other things that went down last week, so we didn't have that.
So when are we doing it?
I don't know. I honestly don't know. I honestly don't
Administration
know.
drills.
Yeah, there was some. We'll say that there was some.
Tahoe's involved.
Sure, we'll go with that. Then
Me either.
you're probably better off.
Not getting it.
I suppose it's a car. The Moore's car.
The idea here, guys, is that you've all dealt with these before. You've all used these before. What we're looking at is how can we start to use these bits of information in a geometry class so that way when we do start working with what are called proofs and stuff, how can we string together logic thought? And that's all the stuff is for. Okay, quite honestly, it's all for logical thought. All right. I think I only have one more example for you. I would like you to try and turn this statement, generic statement, into an if-then statement. I want you to turn this into, write it out, and then we'll give everybody a shot here, and I'll probably you can give me your example in a sec, all right? So what I want to do is take this statement, perpendicular lines intersect. No, I want you to turn it into an if-then statement. I want you to turn it into an if-then statement. Take a second, figure that out. Miss George, what do you got?
I put if lines intersect and they are perpendicular.
Oh, okay. If lines intersect and they are perpendicular, I'm going to throw a counterexample right at you.
I put.
And you know what? That's exactly the same thing someone said first hour.
That's what
Exactly the same.
I said
What'd you say?
If the lines are perpendicular, then they will intersect.
Perfect. That's all it is. Because in this example here, if I throw what you said, Ms. George, what I think whoever was that you, what you guys wrote down, if you did it that way, it totally negated that statement. Okay, so the real easy way to do this is just if lines are perpendicular, and by all means, you can use symbols for these things, guys. You don't have to write the word perpendicular. That's too many letters. Then they intersect. Notice that it's just saying it pretty much exactly the way it started itself out. Okay? I'm trying to think of another example. Because if I say this the other direction, if I say if lines intersect then they are perpendicular, we know that to be false because we can throw that counterexample in there. Tomorrow we'll also say it as if lines are not perpendicular, then they do not intersect. Is that true or false?
True. Wait, no, that's false.
No.
The lines are not perpendicular. That's false. False. It's false. False. It's false.
Aren't those parallel?
Yeah,
Will those intersect?
no.
Not intersect.
So
If lines are not perpendicular, then they will not. So it's a bad example, but you start working through logic, okay? So what I want you guys to work on tonight, I already posted this on the calendar. Let me pull this up here. It was on page, it's 2 sections. It's all in the book. On section 2.1, and then it's going to be section 2.2.
Fix it for you.
Thank you. So the first one is on page 76. I'd like you to roll through numbers 14 through 17, and 82, 3 through 5, and 11 through 18. Now, you guys are going to be really happy to see that there's no solve for x. There's no calculator math that you need to worry about with these. All this stuff next few days is really going to be all logic and reasoning. We're not going to worry so much. We're not going to be worried about algebra again until next week when we come back and we start working with the algebra statements and solving things through and going through there. Yeah. Okay. Okay. All right.